Okay, welcome. In this example, we're going to do a bit more than just find the power series representation and its interval of convergence. We're going to use our series representation to evaluate a definite integral, namely the integral of this function from 0 to 1/2. And if you'd like, go pop it into some calculus solver. You'll see it's not one that we have a technique that we can easily use to evaluate, so we're going to estimate the value of this integral. And we're going to do that with an infinite series. So let's begin by rewriting this slightly. This is the same thing as 1 over 1 minus negative x to the 7th. And recall the key power series that I bring up in every video, so you're probably tired of hearing this by now. But you need to know this, so I'm bringing it up again. And in case there's someone who hasn't seen my videos, there it is. So long as the absolute value of x is less than 1, I know that this will sum to 1 over 1 minus x. So that means whatever here is in this blob position after the negative can just replace every single x in this series. All right, so my power series estimate for this is f of x is equal to 1 over 1 minus negative x to the 7th. So as a series, it's a sum from n equals 0 to infinity of negative x to the 7th to the nth power. Notice this here's my blob, and I put it in the blob spot there. So this is the sum from n equals 0 to infinity of negative 1 to the n times x to the 7th nth power. And then so long as this is less than 1, which implies the absolute value of x is less than 1, this series converges. All that's left to do is check the endpoints. What happens when x equals plus and minus 1? So let's see, when x equals negative 1, we have the sum from n equals 0 to infinity of negative 1 to the n. And I'm going to go ahead and pop the negative 1 here. So negative 1 to the 7th n. So really, this series is just going to jump back and forth between positive and negative 1. Take a look. So our first term will have a negative 1, then we'll have a positive 1, negative 1, positive 1, and so on. So it's going to diverge. Well, it's not going to converge. We know that. And then the same goes when x equals 1. We have 0 to infinity, negative 1 to the n times 1 to the 7th n. That's just going to be the sum of negative 1 to the n. Also will not converge. So this gives me an interval of convergence is from negative 1 to 1, and the radius of convergence is equal to 1. Now let's go ahead and use this infinite series to estimate the value of this definite integral. So what we would like is the integral from 0 to 1/2 of f of x, and that's 1 over 1 plus x to the 7th. So this is the integral from 0 to 1/2 of the sum from 0 to infinity of negative 1 to the n times x to the 7n dx. So let's write out the first few terms and integrate this term by term. So this is the integral from 0 to 1/2 of, well, what would our first term be? If we pop a 0 in here, then we're just going to have 1. If we put a 2 in, we're going to have minus x to the 7th. Excuse me, not a 2, a 1, when n equals 1. If we have a 2, we'll have plus x to the 14th, and so on. There we are. And so I can go ahead and write this as x minus x to the 8th over 8 plus x to the 15th over 15 minus x to the 21 over 21, excuse me, 22. What am I doing? And I'm going to stop here. And I want to evaluate this from 0 to 0.5. So this is 0.5 minus 0.5 to the 8th power over 8 plus 0.5 to the 15th power over 15 minus 0.5 to the 22nd power over 22. And so this is an estimate, I should say. I'm going to stop here. The first 4 terms of this series. Please take a moment, pause your video, and put this into your calculator. Okay, you should have gotten this value right here. Now, using a different technology, in my case, I used Wolfram Alpha. We have the integral from 0 to 1/2 of 1 over 1 plus x to the 7th dx is about 0.499514, and we can see that this is pretty accurate up to 5 decimal places. Oh, actually up to 6 decimal places. Look at that. 499514 if we round. 499514. Hopefully this video gave you some insight into an application of power series representations of functions. Keep calm and math on. You got this.